Okay, hello everyone. This is our fourth meeting, and today we are diving deeper into diffusion models. And by diving deeper, I mean that we will be introducing an alternative way of designing diffusion algorithms, one that avoids the need for Langevin dynamics. It's a long story with a lot of details, so let's just start and see where it goes. Well, I should add that much of the content that you will be seeing here is relying on slides and video from a CVPR tutorial that was given in 2022 by Kirsten Kreis and others. Also a blog by Lily Wang, and I strongly recommend that you take a look at these two sources. Okay, so let's talk about Denoising Diffusion Probabilistic Models, DDPM. This is a name of an algorithm. Let's see how it is being built. Let me remind you how we started. We wanted so much to sample from a probability density function P of X of images. We wanted and still want. This is our main goal here. And so we came up with the Langevin dynamics, which is a promised way to achieve exactly that. The problem is it's defined in the continuum, so we had to discretize it. So we did the discretization and got a Markov chain of operations that take us from pure noise all the way to good-looking images. The problem was that within these equations, we needed access to the score function. And what we did in order to overcome this difficulty is to identify a way of approximating the score using denoisers. One last thing that bothered us is the slowness of this algorithm. It took hundreds of thousands of iterations to converge. And so we came up with the annealing concept, where we start with very blurred version of the PDF and slowly narrow it down as we iterate. This was the path that we did last week. Today, we are going to introduce an alternative that was published in a paper in 2015, 9 years ago. 9 years ago, it is based on a very interesting chapter in statistical physics, and it will give us a bridge that goes from the desire to sample all the way to the algorithm while bypassing the Langevin dynamics. How exactly, you will see. And this is truly very elegant and worth knowing. Okay, this is the paper. This is the paper by Yasha Sol-Dickstein, Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics. A very, very impressive name of chapters that we are not supposed to know, but don't be afraid. It's all math of the kind you are accustomed to. And this is the abstract, and I'm zooming in on it, and I would like to read with you this portion. And just to say something here, this is a paper that was published in 2015, in fact, published in 2016, but released in 2015. When I described methods of diffusion last week, and I brought the papers that initially introduced these algorithms, I mentioned paper from 2019 and beyond. How come I didn't mention this one? Because it's a different approach, because it's not Langevin based, and it is not based on approximating the score using a denoiser. It is based on something else. And yet, let me promise you, the eventual algorithm we will result with will be very, very similar. Okay, so now I'm going to read this yellowish part here, because it will give us the picture of what they are trying to convey. The essential idea, inspired by non-equilibrium statistical physics, is to systematically and slowly destroy structure in a data distribution through an iterative forward diffusion process. So basically what they are saying here, we will introduce some sort of a process where the data is being replaced by noise. This is the forward process. We then learn the a reverse diffusion process. This is the learning part. A reverse diffusion process that restores structure in data, yielding a highly flexible and tractable generative model of the data. So the reverse is the main theme here, and today we will spend most of our time on this reverse. This approach allows us to rapidly learn. So learning is fast and effective. Sample from, so they are able to sample from P of X. And here is something new that we never seen before, and evaluate probabilities. So once you have an image, you can give you the probability of this image to exist. Evaluate probabilities in deep generative models with thousands of layers or time steps. So let's see what this algorithm is all about. Here is the basic idea. You start with a good-looking image. You draw a good-looking image from the distribution of images, and you gradually mix it with noise up to the point where it vanishes and you have pure noise or almost pure noise in your hands. This is the forward process. We will define it mathematically in a second. It will be very clear. There is nothing to learn here. It's very simple. And then we will learn the reverse. We will learn how to carve out an image out of noise in a gradual process. Yes, it will involve a denoiser, but in a different setting. Okay? And one thing should be clear here. If you start with this cat and you go all the way to this noise, when you come back, you do not come back to this image. You come back to an image, a different image, because you are sampling. It could be different as long as it is good looking. So this is what we will be trying to do. Okay. So what I'm going to do now is to define the formulation for the forward process. Okay. Just a second. Good. So here is the forward process defined very simply. You start with x naught. This is x0, good looking image, and you generate sequence of images x1, x2, all the way to xt. T here, just keep in mind, it is 1000 in order to make things concrete. So imagine that I have 1000 steps that take me all the way from a good looking image to something that essentially is noise. Okay. And it will be achieved in a gradual way, one by one. I'll create one image from the previous one, and it will be created using this equation. And the equation says, take your xt minus 1 image, multiplied by a coefficient that is nearly 1. Look, beta is very close to 0, so nearly 1. So you shrink a little bit the energy of the image. You then add random Gaussian noise, okay, canonical noise, multiplied by a very small number, something that is close to 0. Okay, and so you get a mixture of the image slightly attenuated and slight level of noise. This is the way xt is created from xt minus 1. So from x0 we create x1, from x1 x2, etc., all the way to xt. And by the time you get to xt, the noise accumulated is so strong that you do not see any trace of the image anymore, or almost. Let's say it more accurately. Here is our notations that will accompany us today, something that I've already defined in the review in the first meeting. I'm talking about the conditional probability of xt given xt minus 1. This conditional is a Gaussian. It's a Gaussian with a mean and covariance. Look at this. If xt minus 1 is given to us, then all this part is basically deterministic, and it will serve as the mean of xt. Here it is. It's the mean. Square root of 1 minus beta t times xt minus 1. And the variance is the strength of this noise. So basically take this coefficient and square it. This is the variance, beta t. So this is our notation. It's a Gaussian of the variable xt with this as the mean, and this is the covariance. The covariance is a diagonal matrix. That's it. Lovely. Here is a lovely observation. One thing that needs to be made clear here is the fact that I'm defining the forward process, and I will use it a lot, but we never truly compute it. It's not something we will compute. It's something we will use to analyze something else. Okay? So in the spirit of this claim, here is an observation that says, you know what? From x0, you could jump straight into any time point. You can jump from x0 to xt. How? Well, xt itself is created from xt minus 1 using this formula that we have just defined. As it so happens, and we are about to prove it, xt itself can be written differently as a coefficient multiplying x0, the clean image, and another coefficient. Notice the two coefficients sum together to 1 in their squares, just like these. And with another coefficient multiplying a Gaussian vector, you are creating a mixture that will take you from x0 to xt. Who are those alphas? Look at the alpha. Alpha is accumulation of the 1 minus beta. I know it's a bit annoying that 1 minus betas turns into alphas, but this is the common notation in the literature, and I'm just following it. So basically, you're accumulating all the 1 minus beta that were here for t equals 1, 2, 3, all the way to t, and this is the coefficient here. And as it so happens, and it's not obvious, the coefficient that multiplies the additive noise is exactly the square complement of it. So this square plus this square is exactly 1. Okay? This is interesting because it really means that if you want to write the conditional probability of xt given x0, you can write it down as a Gaussian as well. It's a Gaussian with xt as the variable, with mean, which is exactly this term, square root of alpha t x naught, and the variance is the square of this, 1 minus alpha t. Same rationale as before. Okay. One thing that needs to be explained here, and this is delicate, is the fact that epsilon t and epsilon t plus 1 are not totally independent random vectors. In fact, they overlap a lot, because moving from epsilon t to epsilon t plus 1 means that you took epsilon t and added a small fraction of noise. This is the vt that we see here in order to jump to epsilon t plus 1. But we don't need that now, so let's just forget about it. What I would like to do now is to show you that these coefficients are indeed suitable, and this equation is correct. One comment before I go there is the following. Remember that as I go deeper and deeper into the forward path, I end up with xt, remember 1,000 steps, and I'm supposed to get here something that is nearly noise. So if this is the case, then keep in mind that alpha capital T should be nearly 0, so that this coefficient basically says in the final mixture, there is hardly any trace for the true image. You only get noise with a coefficient which is essentially just 1 times the noise. Okay, now let's prove this. The proof itself, I wouldn't say simple, but quite expected. It goes like this. This is the formula for moving from xt minus 1 to xt. But the xt minus 1 itself is created from xt minus 2. So it is, okay? Square root of 1 minus beta t minus 1 times xt minus 2, plus some coefficient, the same beta, times yet another vector, etc. Now xt minus 2 is the creation from xt minus 3, and so on. In a telescopic way, you can write it down all the way to x0. And look at the coefficient that we will end up with. It will be 1 minus beta t square root, 1 minus beta t minus 1 square root, 1 minus beta t minus 2 square root, etc., all the way to 1 minus beta 1. Why beta 1? Because observe that always the index of the image here is 1 below the last index of the beta. So if the index here is 0, this is 1. This is exactly the alpha I promised you. This is the alpha. And this is not the alpha. Yes, this is the alpha. And what you do is the square root of alpha t is what multiplies x0. This is the easy part. Now the question is, what are the remaining elements? The remaining elements are beta t square root times vt, here it is, and square root of beta t minus 1 times this square root times vt minus 1. This is the second term. And then you have vt minus 2 with its coefficient, 1 square root here and 2 square roots outside, and so on and so forth. So you have many ingredients. But here is the main observation. vt minus 1, vt minus 2, all the way to v1, they are all Gaussian IID vectors, and each of them is independent of all the others. And therefore, if you combine many such vectors in a linear combination, what do you get? What do you get?
Another Gaussian?
A Gaussian whose variance is
Another
the same
Gaussian.
as
So let's make it concrete. Yes, you get another Gaussian. Linear combination of Gaussians that are independent is definitely Gaussian. If all those vectors v's are 0 mean, what is the mean of the combination?
0.
0. So the first moment is 0. We are safe there. What is the variance of this combination?
The sum of the variances.
Exactly. The sum of the squares of all the coefficients. Take the coefficients here. Take this beta t. Take this and square it. Take this and square it. Sum everything. And you will end up looking at the variance of the combined Gaussian. This is exactly this sentence here. Okay? So with a little bit of effort, let's write the general expression for the sum of squares of the coefficients here. Here it is. Looks horrible. Let me explain it. It runs backwards from t to 1. Let's assume that we just compute it. So q equals t. So it's beta t times the multiplication from t plus 1 to t. When this multiplication here goes backwards, it's basically 1. This is a convention. So basically, this is 1 times beta t. This is exactly this coefficient. Let's take u equals t minus 1. T minus 1, it's beta t minus 1, which is exactly this, times you run from t to t, 1 minus beta t, exactly this element. And so when Q gets smaller and smaller, you accumulate more and more of those elements just as expected. This is the expression. And I'm claiming that this is exactly 1 minus this alpha t. And if this is true, I'm getting exactly the formula I've shown you. So let's prove that this is exactly 1 minus alpha t. How would you go about proving it? What do you think?
Induction.
Any idea? So here is what we are about to prove. We are about to prove that the expression we have just written, this is the blue part, equals 1 minus alpha t, and alpha t has an explicit form, so the yellow equals the blue. This is what we are supposed to prove for any t. How do you do it?
Maybe by induction.
Indukcja.
Definitely induction. So you check it for 1, and it works. Should I do it? Check me. It works. You do it for 2, and it works. And then you assume that it works for t, and you ask whether it applies to t plus 1. This is exactly the induction concept. So let's do it. Here is the expression for t plus 1. I'm taking the blue part, and I'm replacing t here and t here with t plus 1. That's all. Now, this is a summation. Let's break it into 2 parts. The part that refers to the t plus 1 and the remaining. So the remaining is here. The remaining part is here. It's just the same expression, just running from t to 1. And as for t plus 1, this is beta t plus 1 times reverse. You run from t plus 2 to t plus 1, so it reverse. This is just 1. So beta t plus 1. Beta t plus 1.
Mickey, I'm not sure. I'm not sure we see your pointer. I don't see a pointer.
Any others? Do you see my mouse?
No.
No.
I don't have a solution for it. I had to change computers. I'm sorry. So it's beta t plus 1 plus the entire expression where I'm simply summing from t to 1 instead of summing from t plus 1. The next step to do is to take the inner multiplication, the pi, and extract out 1 minus beta t plus 1, because this is the last item in all the multiplications. So 1 plus beta t plus 1 comes out, and I'm remaining with this expression. Now, the rightmost expression is exactly the expression we had above. So this is exactly 1 minus alpha t based on the induction assumption. So this is exactly 1 minus alpha t, or let's say this is exactly the yellowish part. So I'm replacing it with the yellowish part. I'm opening parentheses, organizing elements, and I'm getting that this is exactly 1 minus exactly the same expression with t plus 1. So it's 1 minus alpha t plus 1. And this is the proof. The fact that you don't see my mouse is a problem, because it will haunt us during this lecture, because I do want to show you where I stand. I wonder if there is a solution to it.
Mickey, you can use the Zoom annotation tool.
I cannot, because I'm using a different computer, and this computer does not give me access to the annotation. Let's proceed. Okay, so I'm summarizing. Those betas are very small. Those betas that define how we move from xt minus 1 to xt. Very small values that are nearly 0. And this is how the process runs forward sequentially. We just saw that by defining alpha t as the accumulation of the 1 minus betas, we get another formula that can give us large jumps forward, only forward. Okay. And here is a typical behavior of alpha as a function of small t. It starts with nearly 1, which means start with something that is pure image and no noise, and it decays slowly all the way so that after 1,000 steps, it is nearly 0. It's not exact 0, but nearly 0. There are many, many strategies for choosing the beta so that the alpha behave this way. What you see here is a specific option that was proposed in the literature. Starts with a very small beta and then slowly grow it in a linear form, but this is just arbitrary. This is part of those parameters in the diffusion that we have to choose in order to make the algorithm work for us. I hope that this is clear. Moving on, here is what actually happens here as we move forward from x0 to x1 to x2, etc. Each of them has a distribution. We start with x0. The distribution is the distribution of the images that we are after. When we finish and we get to x1000, xt, capital T, it's nearly Gaussian, pure Gaussian with zero mean and identity as covariance. In between, we get intermediate distributions that are, we saw this last week. There are convolutions of some sort between a dilated version of P of x and a Gaussian. Another way of looking at it is the following. Look at this expression. The probability at time point xt, time point t, is basically the joint distribution xt x0, and we marginalize over x0. Now, instead of writing the joint, I'm writing the conditional in blue. Conditional is a probability of xt given x0 times probability of x0 in yellow, and again integrating over x0. Why am I doing this? Because the yellowish part is the probability that we started from. The blue part is a Gaussian. We know this is a Gaussian. We have seen it. It's a Gaussian with this as the mean, square root of alpha t x0, and with a specific covariance. In fact, isotropic variance. So it's a convolution between the probability we started with and a Gaussian that keeps shifting based on x0 itself. So it is losing, if you go back to the picture, it is losing details and becoming smoother and smoother up to the point where it becomes a Gaussian. Okay, this was all the forward path, and it is quite easy. And now I'm asking a critical question, and it will open the door to the main discussion of this chapter. Writing q of xt given xt minus 1 is simple. Moving from xt minus 1 to xt is the gradual mixture with the noise. We have an exact formula for it. What about the reverse? What about the probability of xt minus 1 given xt? Can we achieve some knowledge about it? Now, why am I asking? Because if I knew this yellow expression, I can sample. I can sample from x0. How? Here is how. You start by sampling xt. Look at the red star at the beginning in q of xt. I'm sampling a Gaussian. This is so easy. Then, given this, I'm using q of xt minus 1, t, capital T minus 1, given xt, and I'm sampling from the next distribution. And then I proceed, and I'm sampling from xt minus 2, etc., all the way to x0. And once I get to x0, I forget all the path. I take the x0 that I have, and this is a fair sample. This is the path, but I take only the end of it, and this would be a fair sample from P of x0, from Q of x0. So knowing the yellow part will be terrific if we could do it. The question is, how can you achieve it? Now, what is the connection between these two? Change of order between xt and xt minus 1. So if change of order is what we are about, this sounds very much like what Bayes would give us. So let's use Bayes. Bayes says probability of xt minus 1 given xt equals the forward probability of xt given xt minus 1 times probability of xt minus 1 divided by probability of xt. You see, this part is a simple Gaussian. This is the easy part. The two yellow parts, we don't know anything about them, so we are stuck. So what do we do? Okay, this brings me to the next chapter where we start talking about the reverse path. Listen, okay, we move now to the next chapter when we treat the reverse path, understanding that answering properly the question, Just a second. Yes. Okay, understanding that the reverse path enables us to sample. If we answer how to do the reverse, we are well equipped to come up with an algorithm that is serving our need, sampling from P of X. So this is something we have seen before. And we are asking now, what is the probability of xt minus 1 given xt? And notice the change of notations. Now it's P of theta. P of theta to make it clear that this is a learned distribution. This is a distribution that will go backwards in time in order to go from noisy images, less and less noise, all the way to good-looking images. Who are those probability density functions? And the first thing I'm saying is those are Gaussians. Each of them is a Gaussian. We approximate it as a Gaussian. An old paper published in 1949 suggested this result that says if betas are small enough, if your discretization is fine enough, you can assume that those distributions that go backward are also Gaussian, just like the forward ones. Now, this is very pleasant because it really means that this is the probability density function. All you need to find now are the mean and the covariance of this distribution. The mean and the covariance depend on the known portions, so on xt, and they will try to come up with explanation about how xt minus 1 is distributed. This is the Gaussian we are after. So learning is all about learning the mu and learning the sigma. Okay? Let me give you a little bit of intuition. In the forward path, we migrated from a clean image x0 to x1 to x2 all the way to x1000, x capital T. And in this migration, we added slight noise every time with a mixture. And in terms of the PDF, the probability density function, we kept losing details. We blurred the PDF. In the reverse, we will do exactly the opposite. We will have some sort of denoising. It have to be a denoising. And it will have some sort of a sharpening effect. We will sharpen this function gradually as we make our way back to x0. Okay, but this is just intuition. Let's move on. So this assumption of Gaussianity, let me motivate it from a different direction. Just a minute ago, we tried to use base and got stuck. Let me try to use it again. And this time, it will have a service for us. You see, this is the base that we just written. Remember, Q of xt given xt minus 1 is something we know. This is the Gaussian that goes forward. And we got stuck because of those two probabilities, Q of xt minus 1, xt. We don't know anything about them. If we knew, this would have been a lovely passage from the forward to the backward. But here is the thing. First, xt is given to us. So the denominator is a number. Forget about this number. So basically, Q of xt minus 1 given xt is basically multiplication of those two ingredients in the denominator divided by some constant. So we are proportional to this multiplication. Lovely. Now, let's think about those two ingredients. This is a very simple Gaussian. We know exactly how it looks. And this is a distribution that we don't know. But here is what we do know. We do know that Q of xt minus 1 is a very wide distribution that exists in a wide support. Okay? It's a blurry version of Q of x0. On the other hand, the bluish part, if I had to draw it on the same axis, it looks like this. It's almost a needle. Why is it a needle? Please help me. Why is it like almost a needle?
Because beta is very small, it has a small variance.
Exactly, and the beta is the variance of this. So beta being 0.0 something means that this is a needle, and the overlap between the blue part and the red part basically meets the red part in nearly constant value. So basically, it's a Gaussian times a constant. So it's a Gaussian. This is the rational. In fact, if I had to prove this claim, this is exactly how I would go about it. I will claim something about bounding the derivatives of Q here, of Q0, knowing that the other Qs are only simpler and smoother. And by bounding those derivatives, I'm getting some sort of regularity assumption on P of x0. And with it, the Gaussianity claim makes a lot of sense. Okay, so this is just slightly better intuition about the Gaussianity assumption. The bottom line to it is this. This is a Gaussian that we are after. If we find mu, if we find sigma, we are done. Okay? We have to find these two moments and we are done. This is so pleasant compared to the original problem we had, because knowing that it is Gaussian simplifies our life. Now, what I'm going to show you are several ways of coming up with mu and sigma. Several ways, 4 different ways, and only the 5th will be the one that is promoted in the literature and being called DDPM. So several simple approaches, and then DDPM will come and will be the actual method that people are using. So let's dive into it. Okay. So the first option is quite intuitive. It says the following. You are thinking of this probability as a Gaussian. Great. So let's fit a Gaussian to data. Here is what I'll do. Take 100,000 good-looking images. Each of them is an X0. And from each of them, create the complete path that goes forward. Okay? Going forward is trivial. I know what to do. I know exactly what to do. There is nothing to it. I can create all the time steps all the way to X capital T. So I'll have 100,000 such paths. Okay, now let's freeze a specific time point T, and let's take the triplets T, xt minus 1, and xt. I have 100 such triplets of the image at time point T minus 1, and the later one that emerges at time point T. I have many, many such triplets. Let's fit a conditional Gaussian to them. Okay, let's learn the neural network that will get xt and will fit this Gaussian. Let's learn the covariance that will get xt and will fit this Gaussian, such that this Gaussian loves the probabilities of xt minus 1. Let's write it down as an expression. This is classic maximum likelihood. It goes like this. Sounds horrible, very simple to apply. Here is what I'm saying. This probability applied to the actual examples that I have, and remember, I have 100,000 such examples. I want these probabilities to be as high as possible. So I'm searching for the theta that will make this Gaussian such that it loves those vectors. It finds that the probability of those xt minus 1 given the xt are the highest they can be. So instead of one thing I have to say, since I took 100,000 examples and they are drawn IID, the probability of their joint behavior is the multiplication of their individual probabilities. So this is why I have a multiplication. Now, instead of maximizing the product, let's maximize the sum of the log. Basically, I took a log over this expression, and log replaces multiplication with summation. So maximizing the log probabilities. Now, here is the thing. These probabilities are Gaussian. I have explicit form from them. So, you know, it's a constant. The constant is horrible. It has all sorts of elements in it. And sigma, by the way, this sigma theta, with a determinant appears there. And then it's an exponent times some quadratic expression. Take the log of it, and you end up with this. What do you see here? It's xt minus 1 minus the mean, xt minus 1 minus the mean that is computed over the same path with xt, okay? The kth element versus the kth element, and weighted with sigma minus 1 in between. This is the element that sit in the exponent part. If you are missing the minus here, don't worry, it's not vanished. We replace the max with mean. So we are now minimizing this expression. And yes, we have another term, the term that says there was a coefficient in front of the exponent. You took the log of it. So it's the log determinant of this. Okay? Now you have to find the theta that will make this expression happy, which means minimize it. And you found your best fit for a Gaussian. Now here is, yes, please.
Why are you using inversion for the sigma theta?
It simplifies our life. And you'll see that it will vanish in a minute. Okay, so instead of writing everything in terms of the sigma theta, I'm writing things in terms of sigma minus 1 theta. But again, the next sentence is going to change everything. And here is the next sentence. 99.9% of the diffusion algorithms that I'm familiar with make an assumption that says sigma theta is too complex. Let's just assume that it is a scalar that is to be learned times identity. So basically, this matrix is assumed to be diagonal with a constant value on the diagonal. So things are now much simplified. Instead of learning sigma theta, I'm learning a parameter, a scalar. Now, if I'm coming back to this expression, plugging here 1 over sigma squared, sigma t squared times identity, can jump out here. Log that is very simple as well. sigma minus 1 has 1 over sigma t squared in all the diagonal. The determinant of it is the multiplication of them. So basically 1 over sigma squared to the power n, and log takes the n out, and you log it, you get n times log of 1 over sigma t. This is it. Here is the expression. This is the expression we have to minimize. So now the unknowns are the theta that govern the computation of the mean, and this scalar here that sits here and sits here. Let's assume that sigma is known to us. Okay, let's just freeze sigma for a minute and ask, who is mu? So basically minimizing this with respect to mu means that this element play no role, and I'm getting that this is my minimization. Look at it. What is it? It says, take your xt. For every example k, you have capital M, 100,000 such examples. And I'm searching for the neural network that will take xt and will clean it up to the point where it will look closest to xt minus 1. It's not the regular denoiser. It's a denoiser that removes a slight fraction of noise. Is it clear? Yeah, I'm removing only the layer of the noise that take us back from xt to xt minus 1. This is a denoiser, but a slightly different kind of a denoiser. So denoiser, as expected. Now, if the denoiser is known to us, what is sigma t? Take the expression above here. Now optimize, think about 1 over sigma t squared as my unknown, as, I don't know, let's call it z. So it's z times this expression plus minus n times log of z. Now, if you take derivative of this with respect to this z, what do you get? This coefficient here drops out. So you get all this expression with the sigma here. And here, it's log of 1 over z. Sorry, the log derivative is 1 over z. So with a little bit of algebra, you get that sigma t squared is exactly this expression. What is it? It's basically take your denoiser performance, divide it by the number of examples, divided by the number of samples in each of the vectors here. And basically, it's the mean squared error per pixel. And this is my sigma t squared. So sigma t squared is nothing but how good is your denoiser? This is the spread around this denoiser. So easy. And yet, this is not the approach taken in the literature. I have not seen one paper do it. And the claim is it's not worthy of trying it because denoisers that are trying to remove only a small fraction of noise are not performing so well. This is exactly the next sentence. Moving from option 1 to option 2, people say, listen, it doesn't work. You cannot come up with a denoiser that will be reliable in removing small portion of noise from xt to xt minus 1. We are familiar with denoisers that can take the image xt and go all the way to x0, or at least estimate it. And here we are trying to do something different. So the obvious question is, can we change our language and work with regular denoisers, one that go all the way to x0? So here is one possible such answer. And the answer says, you know what? Let's repeat everything we did with a small twist. Let's now take 100,000 good-looking images x0s, create all the chain of xt's from them, and now keep 4 elements, 100,000 such 4 elements of really true image, the time t minus 1, and the temporal point t itself. And now let's do the following. Let's start by designing a denoiser that is regular. Look, these are the notations we have. This is the denoiser with parameters theta that takes xt and tries to estimate x0 from it. You have the data, you have the clean images, you have the noisy images. Try to make your best estimate. Basically MMSE or whatever you want. Here, I'm not really cleaning to the MMSE. So just estimate x0. Now that you have x0, here's what I'm suggesting. Mu, the mean of xt minus 1 given xt, will be a linear combination of the noisy image xt and the denoised image x0 hat, the output of the denoiser. Why am I doing this convex mixture? Because once I cleaned the entire image, I want to go back and return much of the noise, but not all of it. And so this A is supposed to be nearly 1, slightly smaller than 1, okay, in order to come back to xt minus 1. And now I need to design this A. How would I do this? My option here, I have 2 options. Let's start with the simpler option. And the simpler option says, you know what? Take this expression as is plug it in a least squares. This is all the mu minus the image it tries to get to. So this is the mu trying to get as close as possible to xt minus 1. The unknowns here, the unknown here is the scalar at. That's it. Because this image xt is known to us. The denoiser is known to us. This is xt minus 1 given to us from the examples. So we can actually do least squares and find the optimal a. Once you have found the optimal a, use it. And in fact, following the same rationale as before, once you have it, the performance of this denoiser, combined denoiser, is the sigma t. Take the mean squared error of this per pixel, and this will serve as the sigma t. So this is option 2a. Very simple to apply. I have not seen this done in the literature, and I don't know how it will work. Let's move to option 2b. Basically relying on the same formula, but doing something slightly more involved. Here it is. This is the formula, and it says the following. Let's try to fit the level of the noise in the denoiser here to the actual noise in xt minus 1. So here it is. This is how it goes. Remember, xt minus 1 is a combination of x0 and noise. And this is the strength of the noise, square root of 1 minus alpha t minus 1. Okay? On the other hand, xt minus 1 hat is exactly this mu. It's at times xt plus 1 minus at times x0 hat. Now let's assume that x0 hat is x0, which is crude, but this is the assumption I will make. So basically, this is a clean image, and this is the image xt. So basically, at is multiplying, instead of xt, I will write down expression that is very similar to this. Square root of alpha t x0 plus square root of 1 minus alpha t epsilon t plus a deterministic part. So what do we see here? We see that epsilon t is multiplied by at and by square root of 1 minus alpha t. This is it. This is the level of the noise in my formula, xt minus 1 hat. This is the level of the noise in the original formula of xt minus 1. If those two are equal, it implies that this is the at you want to use. Now, I could have done something different. I could have said, you know what? I mean, look at the equation. The equation of xt minus 1 says two things. I have a coefficient time noise and a coefficient time x0. In fact, I have here a coefficient time noise and a coefficient time x0. So basically, I could have demanded an equality between the two red parts. If you do that, you get a very similar expression, slightly different from the above one. The two are different, and maybe you want to take something in between, God knows, okay? And for the sigma t, you can, so this would be the mu. Once you have done it, simply plug in the formula that you got, and you get a formula. By the way, this formula is formula that is being used in DDPM. So we derived it from a different direction, but it is being used. And as for the sigma, I don't want to drag too much here. Basically, the message is this. If xt is a combination of xt minus 1 plus level of noise beta t, and we multiplied xt by 80, so 80 times square root of beta t is the level of the noise. This is the rationale here, and so this is the formula for sigma t. You always take the beta t and multiply it by something that is slightly smaller than 1. Okay? And by the way, this is exactly a formula that has been used in yet another approach that is called DDIM, which we will talk about quite heavily in a later chapter. Okay. So this was option 2b, let's call it. And let's move to more intricate and smarter options. Option number 3. Let's do something strange. I'm searching for p theta of xt minus 1 given xt. Let's now assume that x0 is given to us. Now, this is totally stupid because x0 is not given to us. If it would have been given, then the game is finished. We have x0. Who needs anything else? So yes, we will assume the knowledge of x0 in this expression, and later on we will find a way to remove it. And now the question is, what about this expression? Can we do something about it? Turns out that something beautiful is happening here. Here is what happens. You see, remember the base formula that we try to use, moving from the forward to the backward? It's the same thing here with only one change. x0 is given in all the ingredients, given x0, given x0, given x0, and given x0. Nothing is changed here apart from this addition of knowledge of x0. And now, this is truly beautiful because this is Gaussian, as we will see in a second. This is Gaussian, as we will see in a second. This is Gaussian, as we will see in a second. And so I'm claiming that the combination of the three, Gaussian times Gaussian divided by Gaussian, is a Gaussian. And so I can actually get a closed form expression for this, because all of them come with closed form expression. Now I have a question for you. If this is a Gaussian, this is a Gaussian, and this is a Gaussian, how come the computation here amounts to yet another Gaussian? Why is it true? Why is it true?
Because the form of the Gaussian is the exponential, and if you multiply and if you divide, it remains the exponential.
Exactly. It's all about constant time exponent of a quadratic expression, and multiplication of those functions remain of the same form. Division by such a function remains of the same form. And yes, it will be a Gaussian. So basically, in analysis of it, all you have to do is to show me who is the new mean, who is the new covariance, and you're done. So let's talk about these three ingredients, because they are clearly building everything here. So who are the three? Let's start with the denominator, q of xt given x0. Who is it? I remind you that in the forward path that does the large jumps, given x0, you can get to xt in a pure Gaussian way, and it will come up in a second to the slide. Let's see. Yes, here it is. This is the formula that goes from x0 to xt with the help of those alphas. So what am I saying? This is a Gaussian. The mean is this, square root of alpha t times x0, and the variance is the square of this, 1 minus alpha t. The same for q of xt minus 1 given x0. The very same thing. It's another Gaussian. We know exactly how it looks. This part here, q of xt minus given xt minus 1 and x0, is slightly more intricate. You see, we do have this formula that moves us from xt minus 1 to xt. And so what I'm saying is that this probability that I'm trying to figure out, you can omit the x0 from it. Just forget that it exists here, and write down the same expression without x0, and obviously it becomes a Gaussian. Now, why is it true?
It's a Markov process.
Exactly. You don't need to know x0. If you know xt minus 1, you know everything there is to know in the chain, and x0 adds nothing. And so it's a Markov chain, and as such, it becomes this simple Gaussian. So people took these three Gaussian, did the algebra, and got to this horrible looking expression. What do you see here? It's a Gaussian of the variable xt minus 1 with a coefficient multiplying x0 and a coefficient multiplying xt. Betas and alpha t minus 1 and alpha t are all mixed in order to make this happen. And this is the variance. Now look at the variance. This is exactly the formula we've written in option 2b. Okay? So it's not a mistake. It's not a coincidence, I would say. Okay, so we have this expression. What do you do with it? First, I want to draw your attention to the following. You can replace the appearance of x0 with epsilon t. Just a technicality. Why? Because if xt is known and x0 is known, then epsilon t is known. So 2 give you the third element. So instead of writing x0, you can replace it with this expression. x0 is basically xt minus square root of 1 minus alpha t epsilon t divided by square root of alpha t. Take this, plug it in, and get a simpler expression. And why am I doing it? Simply because everybody are using this expression instead of this one. So I just wanted to make things clear. Okay, so this is the expression we will work with. And then what? What do we do? And now I'm getting to the climax of option number 3. So again, we have this expression that will come up in a second. It uses epsilon t and xt in order to compute the mean. And it has a variance that is simply a scalar that is computed from the parameters we have chosen. And again, the probability with knowledge of x0 is just like the probability of knowledge of epsilon t, nothing to it. It's the interchangeable. And what I can do, and by the way, people have done it, is to say, you know what? I don't know epsilon t. I don't know x0, but I can apply a denoiser. I can apply a denoiser and get epsilon hat t, the estimated noise or the estimated image. And once I have it, for example, here is a denoiser that estimates x0. I'll plug it in here, get the estimate epsilon hat, and forget that it is not the real one, plug it in here, and use it as the Gaussian expression that I'm so much after. Okay, so a denoiser is involved. What kind of denoiser? The kind of denoiser we love to use, the one that removes all the noise. So yeah, it boils down to the same language. Apply a denoiser, do all sorts of combinations, come up with a mean, and you have a Gaussian, sample from it, and keep going down towards x0. So this is the option number 3. Let's do option number 4 and then have a break. Option number 4 says, okay, this is all fine, but what you did here in replacing epsilon t by epsilon t hat is just wrong. You cannot do that. You have to do something slightly more delicate. So let's fix it. Here is what I'm going to do. Okay, I'm going to do the following. Those two probabilities we agreed are the same. It doesn't matter whether it is x0 that is known or epsilon t that is known. Okay, good. Now you want to remove the appearance of epsilon t or the appearance of x0, marginalize, integrate over it. This is the proper way of doing things. So you take this probability. Notice this is the known Gaussian that we have above. So pleasant to work with. This is the probability of epsilon t given xt. We'll have to find out what it is. And with this integral, we will end up with this Gaussian that we are trying to work with. Okay? So the question is what to do about this. What do you think? What shall I assume about this? First, in words, what is this expression? What is it saying? The red part. What the meaning of it? Yes, please.
להגיד מה הרעש שהוסיפו לתמונה?
Let's say it exact. So given the noisy image, when you apply a denoiser, you get an estimate of epsilon t. But in fact, there is a distribution of epsilon t that could explain the noise in this image. So this is the distribution of the possible noises that exist in xt. Okay? If there is such a distribution, what is the role of denoiser in this sense? Where is it sitting in this distribution? What do you think?
The denoiser is the MMC
expectation.
minimizer, so it's the expectation.
It's the expectation. So when you have a denoiser, you have the center of the distribution. And now this says, okay, center, lovely. But here's what you did in option number 3. You assume that this is a delta function around the center. This is what we did in option number 3. And this is just wrong, because denoisers do not produce the one and only noise. There could be other noises involved. So what would you do about the red part? What could you do in order to make things slightly more accurate? Please. Any idea?
You can approximate it as a Gaussian instead of a delta. So you give a little bit more structure.
Exactly. And because I'm stupid, I will even assume that this is an isotropic Gaussian, which is wrong. Denoisers do not produce isotropic distribution of epsilon. But let's assume that it is isotropic. So basically, I'm assuming that Q of epsilon t given xt is the denoiser output. I remind you, we have to migrate from the denoiser to epsilon. So this is the formula we already seen. And I'll give it a scalar. And this scalar is something that I need to figure out. Maybe I can estimate it from the denoiser itself. You know, this is basically the MSE. This is the MSE of the denoiser, okay? If the MSE would have been 0, then this would have been perfect. And so if I plug it into the integral, what do I get into this integral? It's a convolution of two Gaussians. It's a Gaussian convolved with an isotropic Gaussian. What do you get? You get the expectation is the one we have seen before, exactly the one we have seen before. And the variance is simply growing by sigma t. That's all. So basically, we are widening a little bit the p theta of xt minus 1 given xt. This is the effect. Everything else remains the same. It's almost the same as option 3 with slight change. This is option number 4. This is where I stop. Again, not an option that is promoted in the literature. And we have now to see the formal approach that takes us to the reverse path. For this, let's have a break of 10 minutes and come back in a second. Okay, we proceed and move now to present the formal approach for designing the reverse path. Okay, so this is the approach that was promoted in the paper I mentioned at the beginning by Sol Dickstein. It's also the method that leads to the DDPM as being practiced today. So it has definitely a justification to be presented, even though it's quite complicated and As you will see, after a lot of fuss, it comes back to something that resembles very much on the option number 3 that we had. Okay, so a little bit of notations to make things clear. We spoke about those forward Gaussians that take us from xt minus 1 to xt. We know exactly how they look. This is it. We can talk about the probability density function of the complete path that starts from x0 all the way to xt. This is the joint probability of the all path given the original image. And because of the Markov chain, it's basically a sequence of multiplications of individual Gaussians from x0 to x1, from x1 to x2, etc., all the way to x capital T. This is lovely. Let's denote it as the probability of the complete path given the clean image that started it all. Okay. And now let's write something very similar for the reverse. And you will see why we'll use this. So in the reverse path, we are looking at Gaussians. We do know that they are Gaussian that go back from t to t minus 1. And they are parametric, as already mentioned. And again, we can talk about the probability of the complete path. Here it is. This time, think about how it is generated. You start by drawing a Gaussian from x capital T with this probability. From it, conditionally, you generate xt minus 1. From it, xt minus 2, all the way to x0. This is the joint probability of the complete path as it was created from capital T to 0. Okay, and again, the notation, very simple. It's a probability of the complete path from 0 to t or t to 0. It's the same thing. Okay, we will be very much interested in p theta of x0. If you think about it, this is what we are after. This is the probability density function of the true images as the generator thinks about them. In fact, what we would like to do is to make sure that this probability loves good-looking images in the sense that it assigns them with high probability. But this is too soon. Let's just concentrate on this expression and write the following. I'm taking this joint probability, or in this short notation, p theta of the complete path. It is equal to the probability of all the path given x0 times the probability of x0. This is strange because it anti-causal in the sense that it was not created this way. It's not that x0 created the path. In fact, x0 is the outcome of the path because we started from xt. But in terms of math, this is valid. We can write it down. Okay? So here is an expression that resembles exactly what we have written in the previous slide, but this time thinks in terms of the reverse. And here is a simple observation, nothing to it really. And it says that if you take those two probability density functions and compute the Kullback-Leibler divergence between them, let's see if it comes in a second. Here it is. The Kullback-Leibler divergence between the forward probability of the complete path given x0 and the backward probability given x0, the distance or divergence between them is necessarily non-negative because of the definition of Kullback-Leibler. It cannot be negative. And here is an explicit expression of it. It's basically an expectation over the first distribution. The first distribution basically is the distribution of all the paths that started from x0 and ended up with whatever they did. And log of the first divided by the second. This is the definition of Kullback-Leibler. Now, I'm taking the denominator. I'm doing now a little bit of algebra. Bear with me, very simple steps. I'm taking the denominator and replacing it with the joint of the complete path, including x0, divided by p theta of x0. So the division actually put p theta x0 on top in the nominator. Okay, it's the same thing. This divided by this is this. We have seen it just a slide ago. Good. Now let's break it into two parts. Log of multiplication is sum of two logs. So here is the first expectation of the first term here divided by this term, plus expectation of the same kind over the log of p theta of x0. And now I can take this expression and move it to the other side. So moving to the other side says minus this must be bounded from above by this expression. Okay? Now, please have a look with me at this expression. And I'm saying that it's actually something that can be simplified. Why? What do you think? How can I simplify this expression? How can I simplify it?
conditioned on x naught.
Say again, I didn't hear.
It's conditioned on x naught, so it should be
yes,
a
exactly.
constant.
So exactly, exactly.
The score, I think.
I don't care what's sitting here. X1 to t play no role here, and x0 is considered as given. So if it is given, there is no expectation. So basically, this is exactly the same expression without any expectation. Okay, good, lovely. And now let's take the two sides of this inequality and do the expectation of the two sides with respect to x0. Here it is. Expectation with respect to true images, expectation with respect to q of x0 of this expression with a minus, just as in place, is smaller or equal. If I now add the distribution of x0, then I'm removing the knowledge of x0 from here, and then that's it. Nothing else changed. This is an expression I would like to work with. And here is the message. As it so happens, I would like very much to minimize this expression. Why? Let's read in words what this expression says. It says, run over many, many good-looking images, because this is the expectation over Q of x0, running over good-looking images from the true distribution of images. And for them, I want the probability of those images to be as high as possible. So being high probability implies that the log of the probability will be high as well. And by having a minus sign, I'm actually saying, give me the minimal value. Minimal value implies high probability, just as I told you. In fact, if you think about it, a more elegant way of explaining it is the following. What you see here is closely related to the Kullback-Leibler between Q, the true probability of x0, and the fake one, the one that the generator creates. This Kullback-Leibler between the two is an expectation over the distribution Q, just like here, of log of the first divided by the second. If you think about it, take this and break it into two expressions. It is expectation of, with respect to Q of x0, of log Q of x0, which is constant in terms of the theta. So this is the constant, minus exactly this. So basically, up to a constant, this is exactly the Kullback-Leibler divergence between the true distribution and the one that we are learning. So minimizing this amounts to minimizing this, and we are trying to make the two as close as possible. Okay? So I'm summarizing. Instead of minimizing this, I will minimize this. This is known as the variational bound. It is upper bounding this expression, and up to this constant, it's never negative. We do know that. So minimizing this pushes down this and hopefully achieves our goal. Okay? So this is what we are doing. Instead of minimizing the left-hand side, we minimize the right-hand side. This variational bound, it should remind you somewhat of what we do with the elbow in variational autoencoders, very similar. Okay. And so I'm marking this as the first approximation, in the sense that we are not serving our goal exactly, we are replacing our goal with something that is more manageable. So from now on, I'll take this expression and massage it to the point where it will become clear what to do with it. Okay, so here is the expression, and I'm writing it now down in a clearer way. It's an expectation over this distribution, here it is, of log of the division, and I remind myself that in the nominator, this is exactly the chain of operations that take me all the way from x0 to xt. Given x0, given x0, you produce x1. Given x1, produce x2, etc., all the way to xt. This is the nominator. As for the denominator, we have written it as well. Draw at random x capital T. From it, draw at random xt minus 1, etc. Go backwards all the way to x0. So this is an explicit way of writing things. And now I'm coloring things. First, referring to the yellow part, all I want to say here is I'm not going to drag it anymore because it's annoying. So let's just replace it with stars, okay? The blue parts, it's a log of multiplications and divisions. So I will break it into three elements. The blue part is here. Here it is. Expectation of something, log of this divided by this. Here it is, Paul. Okay. The green part is here. It's with a minus sign because it is in the denominator. And all the rest refer to the remaining elements. And notice that we are very careful here with the indices. We run from t equals 2 to capital T, so that we start from T1 to 2, 2 to 3, etc., just like you see here in the white. And here we start from 1 to 2, 2 to 3, etc., all the way to T, exactly as expected. Lovely. So nothing really happened, just organizing the expression more elegantly. Let's proceed with this massaging. I'm not touching the first. I'm not touching the second. I'm changing the denominator in the third to include the knowledge of x0. What do you think? Why am I permitted to do so?
It's a Markov chain.
It's a Markov chain. And so knowing x0, don't knowing x0 is futile, means nothing to us. Now, why have I done it? What do you think? Why have I done it? How can it help? Let me give you a hint. Look at the denominator. The denominator goes back. The probability is reversing, moving from T to T minus 1. In the denominator, we are still stuck in the forward from T minus 1 to T.
Base.
Why? Yes, please.
You would like to use the base rule.
Exactly,
and
which is exactly what I've done here. I'm now plugging base as I did before, okay? And now I'm reversing the order here as should be with base, with 2 additional multiplication and division so to fit the base. And the expression is exactly the same. It's not approximation, it's exact, okay? Let's proceed. This is what we got. Now let's massage it a little bit more. Let's break the third element into 2 parts. The first element in the denominator divided by the first in the denominator. Both of them think in terms of going backwards. And then I have an additional part of these 2. Hopefully it will come soon and we'll see it. Let's see. Okay, so I broke the third element into 2 portions. The first is this divided by this. Here it is. Backward and backward. And the second part, the second element takes this expression divided by this expression. Now, it may look very rich, but in fact, it's a very simple expression because there are a lot of cancellations here. Let me take you through this expression. It's an expectation over sum of log of divisions. All of them are probabilities given x0. You run from T equals 2 to capital T with these. So basically, in the denominator, you have x2, x3, all the way to x capital T, all of them given x0. And in the denominator, you have x1, x2, all the way to T minus 1. So x1 remains, xt remains, all the rest are canceled. And this is what we got. And so I'm continuing, and I replace this with the yellow part that appears here. It is a little bit more simplified. Now I notice that this expression here,
Mickey,
yes, please, Chen.
The denominator of it should be 1 minus T, right? T minus 1, right? Not 1.
Have I done it
In the
wrong?
yellow part.
No, it should be 1. It should be 1 here. It's x1 given x0 that doesn't exist in the denominator,
Okay,
and therefore
okay.
it's
Sorry.
Yes, it's x1. Now notice that the denominator here, x1 given x0, is exactly the denominator here is exactly the denominator here, so I can cancel them because one is the minus of the other. Okay, and so now let's take this expression and squeeze it into the yellow by putting p theta of xt in the denominator, and this brings me to this expression. So as promised, I'm coming back to the previous slide. I know it's tedious, but we are coming to the conclusion in a minute. So I took this expression and squeeze it into this denominator. This remains the same, and let's see what I'm saying. So this is the element that lost one of this, the denominator. This is why it has a minus, because, well, it has a minus. And this is the expression we saw where we merged. And this is the main part, which shows the reverse sequentially all over the path. Okay, now what can I say about the 3 ingredients? First, p theta of xt is a pure Gaussian. It's not really learned. It's a pure Gaussian IID canonical. Q of xt capital T given x0 is also a Gaussian, nearly a Gaussian of the same flavor. So basically the 2 are the same distribution. So basically it's log of 1 is 0, and that's it. This is dead. Okay. The third part looks like a sequence of Kullback-Leibler divergence between 2 distributions. In fact, it would have been exact Kullback-Leibler if the expectation here would have used the same expression as denominator. So it's not exact, and you have to develop it, and you can show that it is related to sequence of Kullback-Leibler divergences. Between what? Between the backward as this formula says, which we have a closed form for. I remind you, we have an expression for this, and the learned approach. What about the second term? Honestly, I don't know what to say. People just neglect it, okay? So we have an approximation here that says, I don't care. And we have an approximation here that says, this is not exactly the Kullback-Leibler, but let's assume that it is. And with these assumptions in place, here is the bottom line. Our optimization, you are trying to minimize this expression. Basically, you are trying to bring this distribution as close as possible to this distribution, okay? Q that goes backwards wants to be as close as possible to the p theta, which is exactly what we did before. Let's see how. So here it is in a second. This is why I changed computers, because the slides keep getting stuck. So the variational bound that we have is essentially sum of Kullback-Leibler divergences, so it seems, or approximately, between the yellow Q's that has closed form. This is the Q. I remind you, we know exactly everything about it. We know the variance, we know the mean. The mean itself refers to epsilon t as known because x0 is known. And then we have the blue part, and the blue part has a learned mean and a learned variance. Now we try to make the two Gaussians best fit. What would you choose for sigma t squared? What do you think? I want the blue Gaussian to be as close as possible to the yellow Gaussian. What would you do in terms of sigma t?
A naive approach would be to try to take the same thing exactly.
It's not just the naive approach. It's the only approach that makes sense. You have to choose it. Any other choice will just ruin what you are trying to achieve. And why not? Because it's so easy to choose this equal to this. By this decision alone, you have already made a large portion of proximity between the two. And now you have to fit the first moment. So here's what you're supposed to do. You take the first moment here in yellow, and you say to the first moment in the learned machine, do your best to fit it. What is it? It is training of a denoiser. Okay? It is training of a denoiser of the same sort we have seen before. Okay? And so these are the two choices. I'm sorry for the shift in the slide. These are the two choices we make for sigma and for mu. Now let's make a few more steps around this in order to explain what's happening here. Okay. You try to minimize the sum of Kullback-Leibler divergences between these two distributions. This is what we saw that we have to do. The sigma t, we know exactly what to do about them. This is what we are minimizing. Now, this mu doesn't have to be a general expression. In fact, we can write down mu as an expression that has the same form. I mean, we have access to xt. We have access to beta, to alpha. So we can actually write mu theta as everything with one change. Epsilon should be epsilon hat, the estimated epsilon. This will be the learned machine. And now take this and plug it in here, and you'll get this expression. Look what happened. The xt here drops with the xt here, and I'm getting that 1 over the square root of 1 minus beta squared comes out in squared. So here it is. 1 over sigma t squared remain in the place. Beta t comes out in squared. 1 minus alpha t comes without the square root, and it is epsilon t minus epsilon t here. This is exactly a denoiser design. You show me the true noise, and I'm trying to fit the noise that I'm estimating so that I'm getting as close as possible to it. And by the way, this sigma t here, I have an expression for it. So let's squeeze it in. Let's push it in, and we get this expression. Very simple. The 1 minus alpha t in the denominator cancels with this, and we replace it with 1 minus alpha t minus 1. And this is the loss that needs to be minimized in order to find the best denoiser for this task, okay? This is what DDPM wants us to use as the ideal denoiser if we believe the expressions that we derived. And the denoiser that we are designing will get a mixture of clean image and noise in this formula with the proper alphas. It will know the time step t, it will get it encoded somehow, and it will estimate epsilon hat t. And this epsilon hat t tries to make sense in the sense that it will be as close as possible to epsilon t. And what I'm saying here is that this expression tells you how much effort to put in every time point for your denoiser, which time points are more important than others. And what people notice that if they work with this expression, they do not get the best performance. And arbitrarily, in the literature, they have replaced it with just 1, basically saying the constant 1 replaces this coefficient in the design of the denoiser. And this is what works best in DDPM. I hope that this is clear. So I'm summarizing. Here is the resulting algorithm. You start an algorithm that will sample from the distribution of p theta of x0. You start with a random Gaussian vector of canonical form, and you run capital T steps 1000, and this is a typical number. You draw at random a Gaussian vector, and here is what you do with it. You move from xt to xt minus 1 with this formula where you apply your denoiser, and you add this noise multiplied by this constant, which we are familiar with. This is exactly the sigma t. Okay? And close the loop, and your x0 is your sampled signal. That's it. And a few comments about this algorithm. First, this is exactly the DDPM. And keep in mind this name because people use it a lot. Denoising Diffusion Probabilistic Model. It's one of the more popular versions of diffusion algorithms. It's not as simple as it looks because you have to choose the betas, and you are very delicate about the betas, and you have to design your denoiser smartly. And if you do not do it properly, then your performance will be impaired. So this is why more data change dramatically the performance of diffusion algorithms. You can train on 100,000 examples. Someone else will train on 1 million, and their performance will be far better than yours. And it is related to the annealed Langevin dynamics. You will see some resemblance, and more than just some resemblance, but I'm not aware of a paper that really bridged the two, but they are definitely looking very similar. Okay. Questions so far? If not, let's proceed to the last chapter, and with this we'll finish today's meeting. The last topic is likelihood estimation. And the issue is this. Okay. So you have just designed your diffusion method and you apply it. And that means that you sample a Gaussian vector, and from it you generate sequentially xt minus 1, xt minus 2, all the way to x0. And then x0 is a lovely, good-looking image. And the question is, what is the probability of this image? And I remind you, in the abstract of that paper from 2015, they claim that they can compute this probability. So how do they do it? This is exactly the topic I would like to discuss. Computing the probability of this generated image. Okay, here's what I can do. So easy. I can actually compute the multiplication of all those Gaussians. I have them. As I generated the image and done the sequential process of moving from xt to xt minus 1, from xt minus 1 to xt minus 2, all the way to x0, each of them is a Gaussian. Each of them involves a denoiser that I computed. So I basically can compute all the probabilities of the Gaussians, multiply them, and I will get this. But this is not what I'm after. This is the joint probability of the complete path. What I need is the probability of the image itself, x0. So what is the difference between this and this? Are they the same? What do you think? Are they the same?
You need to marginalize on most of the path.
Okay, wonderful. Exactly. Here is what I have to do. I have to take this multiplication, which can be done, sequence of Gaussians that introduce each other and very easy to compute. And I have to marginalize with respect to all the x1 up to xt in order to remove their dependencies so that I get x0. And this is quite challenging because let me tell you what we are trying here to do. Here is what we are trying to do. We just created x0 with a specific path. We want to know what is the probability of x0. We have the probability of the complete path. But, you know, there are other paths that could have landed on the same x0. 1, 2, 3, several such paths. What I'm trying to do is to integrate over all those paths. I'm trying to sum the probabilities of all the paths in order to tell you how probable is x0. And this turns out to be quite challenging. Let me show you how challenging it is. Let's try to do an experiment with a simple case where the diffusion has only 2 steps. Okay, so basically it's from xt to xt minus 1, and that's it. I'm stopping at xt minus 1, and I would like to know the probability of xt minus 1. I remind you, xt is drawn from a Gaussian, nothing to it, and xt minus 1 is drawn from yet another Gaussian, where the mean of it is the denoiser activation of the resulting xt coming from the previous step. So here is my marginalization. The probability of xt minus 1 is the integral over the joint, but the joint is the conditional times xt, times the probability of xt, okay, dxt. So this is a Gaussian. This is a Gaussian. I can write them down explicitly. Here it is. This is a simple Gaussian. Here it is in front of you, a simple IID Gaussian. This is a Gaussian around the mean that is computed over the xt that comes from the previous step. And now I have to compute this integral. Now, obviously, I'm not going to compute an integral. I'm going to discretize it. So what do I have to do? I have to draw for a specific xt minus 1 that I want to know what is its probability. I have to draw many, many xt's at random from the Gaussian, plug them into this expression, apply to each of them a denoiser, and compute the expression and basically average. This is what I'm supposed to do. And if I'll do this, I will end up with the estimate of this probability of xt minus 1. Lovely. So you know what? I can draw at random 1,000 x capital T's and compute 1,000 denoisings, and I'm done. 1,000 application of a denoiser. If now I add another time point, for every one of those 1,000 steps, I will have to run yet another 1,000 steps of the other denoiser that comes next. So now I'm looking at 1 million activation of denoisers. I cannot do that. It's impossible. So what do I do? So here is the first simple answer. And the first answer that says, you know what? Yes, p theta of the complete path is easy to compute. So go ahead and compute it. And you know what? It is a lower bound on the true probability, because instead of accumulating all the paths, just give me the one that brought you to x0. And it makes sense. Why? Because I remind you that all those probabilities that run from xt minus 1 is from xt to xt minus 1, from xt minus 1 to xt minus 2, from x2 to x1, all of them are Gaussians, and they are needle-like. They are almost delta functions. So there are not many paths that will land on x0. And so if you assume that they are delta functions, you might as well just take this probability and use it as a bound. This is totally heuristic, and yet this is exactly what is proposed in the literature. Here is a more delicate and more elegant way of doing things. Let me show you the alternative that relies on importance sampling. And with this, I will end today's meeting. The idea is the following. We are trying to figure out what is the probability of a given image, x0, that has been just generated. And we wrote the expression. By the way, the person who helped me understand this approach is Omer Belchasin, and I should thank him. So this is the integral we are trying to do. Horrible, we understand. Impossible to compute, we understand. Here is what we'll do. Let's multiply and divide by the same quantity, which is the forward probability of the path given x0. Since I'm multiplying by two non-zero elements and they are the same, I change nothing. Lovely. Now let's do another step that means nothing, but it is actually crucial. Let's change the order. Let's take this q, put it here, and let's take this p theta and move it there. So here is the expression, okay? You don't notice now, but in fact, something dramatic just took place here. Why? Because this is an expectation, okay? In fact, let me do another step and then mention the expectation. So the first term remains intact. I don't touch it. And then I'm writing explicitly the nominator and the denominator. And I remind you, we have been through this. The denominator first is given x0, q of x1 given x0, and then from x1 given x2, etc., all the way to xt. This is this part. As for the nominator, generate xt, from xt generate xt minus 1, conditionally, etc., all the way to x0. So now I'm saying all this expression that looks so frightening is in fact an expectation over the true probability over the forward process of this expression, okay? Let me highlight this again. What we got now, instead of this expression that does integration over the reverse path that land on x0 and can come in all sorts of ways to land on x0, this does the opposite. It says, give me an integration over many, many paths that start from x0 and go everywhere. This is so much more easy to do because the forward path is easy to compute. And this expression is very easy to compute as well. So here's what I'm supposed to do. I'm supposed to create, let's say, something like 500, 1,000 paths of starting from x0, take me all the way to xt using the forward, which is trivial, and then compute all the numerator elements and the denominator elements. So basically, apply denoisers. And so I told you that you take 1,000 paths. The paper by Sol Diction says 1 would be enough. And if 1 would be enough, it means that 1,000 activation of denoisers and you're done. Okay, so this integrates over all possible forward paths that start from x0. And what am I saying here? P theta, this expression, so you do need to use the epsilon, the denoiser. These are the actual activation that take most of the computations, and the rest is trivial. So with this, I will mention again that it's enough to use one path because of the ergodicity of the expression, and you end up with something reliable. So let's see the algorithm. I remind you, this is the expression, and here is what we do. Here is the algorithm. It says the following. You have an image x naught. By the way, I'm stopping here for a second, and I would like to draw your attention to the following property that just took place here. When we started, we said, you are given x0 that was generated by the machine. Please give me the probability of it. Now we are actually even serving a wider question. You can bring your own image. It doesn't have to be a generated image. And I will find what is the probability of it. I can do that as well. So anyway, you have a clean image x0. Here's what you're supposed to do. You have an outer loop that runs over many drawings of forward processes, capital N such processes. And by the way, N could be 1. And you have an inner loop that runs over the expression here, the elements of the expression. You start with the probability being 1, and you accumulate the numerator and the denominator, basically the first Gaussian that refers to the forward path. These are the elements in the denominator, and here it is. This is the probability. You have the backward probability where the denoiser is being called to the service. You compute this probability and this. You take your accumulated value, multiply by p theta and divide by q appropriately, and keep going all the t steps. And when you finish, multiply by pt. This is a pure Gaussian, just a pure Gaussian. And now you finished one path. With this now, take all the paths, average their probabilities, and you have an estimate of p theta of the image you started with. This is one option. A slightly smarter option says, why are you averaging? I mean, the denominator is the probability of each path, and expectation is all about take this expression, multiply it by the probability of its existence, and then average. If you do that, you get a shortcut. You don't have to compute the denominators here, and you don't have to average. You can sum, you can have a shortcut, which is very lovely. And with n equals 1, we come back to the previous method that says, just compute the denominator once and be done with it, which is exactly what I suggested at the very beginning from intuition. I know that this is delicate and tough. Please have a look at the video later on to understand the details. People rarely use this computation of the probability. It's tough. Numerically speaking, it creates a lot of difficulties because you are multiplying very small numbers. And 1,000 such numbers go to basically zeros, and issues arise, and you have to find a way to overcome them. This is where I stop. Questions?
This is very surprising because from the beginning we